All right, well, welcome back. So in section 2.1, we're actually going to be looking at a classic quote-unquote hard problem that's actually going to be the driving force for our next few sections, as well as some of these early public key exchanges and crypto systems. That is, we're going to be looking at the classic discrete log problem. So this may age me a little bit, but oh well. So anytime I start talking about logarithms, the quote-unquote log sum from Ren and Stimpy immediately comes to my head, and then it tends to get stuck there for a little bit. So for those of you that did not grow up in the 90s, Ren and Stimpy was this classic cartoon on Nickelodeon that most of our mothers probably didn't actually allow us to watch, but we still ended up watching it anyways. And there's this nice little song about this product from Blammo called Log, and it has a very catchy theme song that goes along with it. So it says, it's log, it's big, it's heavy, it's wood, it's log, it's better than bad, it's good. So for those of you that have never seen that or heard that before, I would recommend Googling it so you don't have to hear me sing it. But it's got a whole nice little song that every single time I say the word logarithm, that comes to the back of my head and it sits there for a little bit. So anyway, back to the question at hand, this classic discrete log problem. So as I mentioned, there's a lot of moving pieces in the back of this thing that's going to be this kind of constant annoyance problem that we're going to exploit in a little bit. You know, the idea here is that anytime we have some problem that's going to be challenging or difficult to study, a lot of times we grab onto that thing and try to embed it into some type of crypto system. The idea here is that the difficulty of a problem here will actually assist us in creating some type of secure network in later types of problems. So to start this off, we're actually going to look at the classic log problem, not necessarily the discrete log, just so that we have all of our kind of ducks in a row in this case. You kind of remember back to the days of college algebra or algebra 2. So in the classic log problem, we are looking at equations of the form, let's say 2 to the x, which is supposed to be an 8. And your goal in this case is to identify the x that happens to solve this thing. So in this case, you can see that x equals 3 does the trick, because 2 cubed happens to be an 8. You can push this a little bit farther to look at something like 2 to the x, which is a 64. And you can see that this one does have a solution. In this case, it ends up being this nice little number of 6, because 2 to the 6 is again going to fire off a value of 64. You can push this even a little bit farther, that is looking at larger outputs. So 131072. And if you stare at this one long enough, you can see that the thing on the right is also a power of 2. That is, it's actually a 2 raised to the 17th. So in this case, we are actually solving a logarithmic problem. So the idea is that we are looking at this nice little exponential equation. The output in this case ends up being the correct exponent that's going to fire off that output. So in this case, you can see that this 17 is then viewed as log base 2 of that input 131072, and that's going to fire off the answer of 17. So logarithms naturally come up anytime we're trying to solve an exponential equation. You have something like this. The logarithm is simply defined as being that correct exponent that makes this equation work. Interesting things happen in the continuous case once you no longer start having powers of 2. So the idea is that if you were to look at the equation 2 to the x and you say that this is equal to a 3, now you run into some problems. You can think, well, 2 to the 1 is a 2, and a 2 squared is 4, so that value of x should be somewhere between those two values. And you can actually see that visually. If you were to draw the curve y equals 2 to the x, this is your classic exponential growth. So if I switch colors in this case, let's put a nice little value of 1 at 0. At a value of 1, I get 2 to the 1, which is 2. At 2, I get 2 squared, which is 4. And if I connect the dots, you can see the exponential growth. And on the back side, I'm going to be cutting these in half. So and I connect the dots over there. So I get this nice curve, y equals 2 to the x. So when I'm asking, when is 2 to the x equal to 3? Well, you can draw a nice little line at 3 and try to identify where that intersection is going to occur. In this case, you're going to see that it's some number between 1 and 2, which we just kind of alluded to. The idea is that 2 to the 1 is a 2, and 2 squared is 4. So this output should be somewhere between those two values. So what we end up doing is we identify x to be that very special value that satisfies that equation. We call it this fancy log base 2 of 3, so 2 being the base, 3 being the output on the other side. And your calculator's got some ability to create some decimal approximation of that thing. So you know that this thing is actually going to fire off something like a 1.58496, which seems to work. So this is a rounded version of it, but if you trick that number, shove it back into the exponent, so take 2 to that power, it does fire off something very, very close to a 3. So things are great when we're in this world of continuity, because I can always do this process. If I were to take 2 to the x equals whatever other number on the right-hand side, I draw this nice little curve, slice this line at y equals whatever my output happens to be, and I can find that point of intersection. I can actually do a nice little approximation to see what it's roughly going to be. So you can run any number of processes to try to get a pretty close approximation to that. But we know that we can always easily do that. It's not overly taxing to solve this logarithmic problem on the continuous side. Things become a little bit more challenging when we move to the discrete setting. So there's a little bit of terminology that we're going to start off with in this case. So the idea here is that we're going to start off with a nice primitive root. So that's going to be one of these little values of g that when we cycle through various powers, it's going to create this entire space f sub p. So p in this case is always going to be a prime. And we saw a few of those earlier back when we were looking at the world of modulo 7. The idea is that we knew that 3 and 5 happened to be generators, or these primitive roots, because as we cycled through those things, we actually created all of the numbers 1 through 6, and then we started cycling back on them again. In that case, we actually knew that those were our generators because those things actually had this quote-unquote full order. That is, 3 and 5 both had order of 5. So the starting place in this case is going to be grab one of these primitive roots. That's going to become the base that we're working with. And h is just going to be some non-zero entry, which is actually consistent with the classic logarithmic problem, is that I'm not going to start looking at equations of the form 2 to the x equals 0. That thing doesn't actually have a solution in this case. So same thing here. I'm going to take h's, which are non-zero in f sub p. So the discrete logarithmic problem, which is often initialized as DLP, is the problem of trying to find that very special exponent x that satisfies the following. So g to the x is h, but now I'm adding in this little modulo p afterwards. And that little process of adding the mod p makes this a very challenging problem. And we're going to see some interesting graphs that occur in this case. But the idea here is that I no longer have this nice, exponential curve that I can start crisscrossing things on, because that mod p is going to make this all terrible. It's going to start chopping it all up, and I get this somewhat random look or random situation of all of these little outputs. So for now, let's go ahead and look at just kind of a classic starting example. So something of the form 5 to the x, which is a 6 mod 7. So earlier we saw that 5 was in fact a generator, and we can again see that because if I start taking powers of 5, I know that 5 to the 1, so 5 to the 1 is going to be a 1, or say 5 to the 0 is going to be a 1. I know that 5, stop touching that, all right, and 5 to the 1 is going to be a 5 squared, which fires off initially a 25, and then if I reduce that mod 7, well, you know that 3 times 7 makes 21, so 5 squared is actually going to fire off a value of 4. A 5 cubed, if you do the arithmetic on that one, is going to kick out a 6. A 5 to the 4th is going to kick out a 2. A 5 to the 5th is going to kick out a 3. And then in this case, we can actually do one more to see that 5 to the 6th is going to kick out a 1. We actually know that this has to occur from Fermat's little theorem. The idea is that if we're looking modulo 7, which is a prime number, if I subtract 1 from the 7, I get a 6, and I know that taking any entry raised to the 6th is going to immediately come back to the value of 1. So you can see that we do generate all of those numbers, so 1, 5, 4, 6, 2, 3. If I keep on going, it's going to cycle through those again, so I get a 1, 5, 4, 6, 2, 3, and it keeps on going over and over and over. But because I'm only working in the world of f sub p, I'm going to keep that just that one occurrence of each of those objects. At this point in time, you can actually see what the solution has to be. I'm looking for that exponent that's going to create 5 to something, is going to output a 6 modulo 7. And you can actually see that little guy living right here. So we know that 5 cubed is going to output a value of 6. So in this case, the answer is then going to be given by x, which is a log base 3, log base 5 of 6, which is then going to be that exponent of 3. So that's the notation we're going to use, which is somewhat unfortunate because it looks very similar to the notation that we use in the continuous case. But in this case, we are assuming that everything is done modulo. So we know that we have this particular object, which is going to be connected back to these worlds that we're actually looking at. One of the interesting things to think about right now is that the only solution that works? Back in the continuous case, that is the only one, because we have this nice little one-to-one function, and what's going to happen is that we get that singleton value for my x that's going to output that output of 3. That is the only one that works, that little intersection node right there. If I look back at this world, I can actually come up with a few other situations or a few other x's that happen to kick out that same value of 6. And it's actually connected back to this world of this 5 to the 6th being a 1 modulo 7. The situation here is that if I were to take that exponent of 6 and add it to the exponent of 3, so if I take those two numbers, you can see that if I have a 5 raised to the 3 plus a 6, well, that's just really a 5 cubed multiplied by a 5 to the 6th. Well, a 5 to the 6th is going to fire off a 1. The 5 cubed we know is going to make a 6. So that thing at the end of the day is again going to kick out an answer of 6. So in general, any solution to this thing is going to be of the form 3 plus some 6k. So those become all possible solutions for this particular discrete log problem. The somewhat annoying thing that occurs in this case is that initially everything was done modulo 7. So this congruence is viewed modulo 7, but the solutions that actually come out are then viewed modulo 7 minus 1, i.e. mod 6. And that's going to be a fact that we're going to see a little bit more later. The idea is that this original thing is viewed modulo p. This logarithm is actually defined modulo p minus 1. So there's a slight change in that we go from a value of p to this thing being viewed p minus 1. A couple other things that do come into play as we start studying these particular equations is that we start with this assumption that g is a primitive root. If we were to change that up, some interesting things are going to occur. The idea is that if I looked at 6 to the x, and if I ask when is this going to fire off a 6 mod 7, well, in that case, that's easy. You can see that the solution here is going to say that x should be a 1. If you change that 6, though, to something else, so let's say I look at 6 to the x and ask when is that going to be a 2 modulo 7, well, if you start taking powers of 6, you get 6 to the 0, which is a 1. You get a 6 to the 1, which is a 6. You get a 6 squared, which is back to a 1. And you're going to see that that's going to cycle from 1, 6, 1, 6, 1, 6, 1, 6 over and over and over. The idea here is that that value of 6 actually had order of 2. So we know that that thing is not going to be a generator for my original collection of f sub 7. The idea is that this is only going to create the values 1 and 6. Whereas the number 5 actually cycled through and created all of those entries in that field. So here we're missing some terms. So sometimes this congruence will have a solution, and other times it won't. So we can actually rephrase this discrete log problem by allowing g to be any entry, but the issue here is that this thing may or may not have a solution. If it is a primitive root, then we know that this thing is guaranteed to have a solution. If I switch it to some non-generator, I may have something that's actually going to fire off as a non-solution. You can see that I can actually change that base to something else that is a generator. So we did the situation where the base was a 5. Well, there actually is another generator when the p-value is 7. So in this case, those are values of 3. So if I wanted to solve this thing 3 to the x being 6 mod 7, well, what's going to happen here is that I can, again, brute force all of those values. We know that 3 is a generator, so I'm just going to wait until that correct value fires off. In this case, it actually fires off with the same value of 3, because 3 to the cubed, or 3 to the third, I should say, is then going to, again, reduce back down into a 6. So it's a nice little thing to see is that you can have some solutions. We have to, at least right now, run this horrible brute force process to actually identify these things. Later, we're going to start looking at a few simplifications to that, but it is still a generally hard problem. we don't have a super awesome, elegant way to actually identify these discrete logarithms. And that's what makes this a nice hard problem that we're then going to try to exploit later on.